Hey everybody, welcome to Unit 7, Physics 40S, Lecture 3. Today we're talking about the laws of resistance and also about power and work associated with current electricity. So in our booklet we are on page 35. So, first law of resistance is that there's no Fight Club. I always tell that joke. Nobody ever laughs. Resistance is proportional to the temperature. This is true with most materials. The hotter something is, the more it offers a resistance. Okay? The second one is resistance is proportional to length. Think of a resistor and then a whole bunch of resistors in series, so making a longer chunk of material, and the total resistance, you would just add the individual resistances together to get a larger value. So the longer something is, whether it's straight or curled up, the greater the resistance. And the third one is that resistance is proportional to 1 over the cross-sectional area. We're going to assume that all our resistors are like cylinders. So the cross-sectional area is the area of a circle, pi r squared. So we're saying that if you have a larger cross-sectional area, you are going to have less of a resistance. And you can think of that as a whole bunch of resistors in parallel, right? So they get fatter and fatter, and there is more current that can flow through. So larger cross-sectional area, less the resistance. And in fact, you can put that together before we look at resistance 4 and think of a light bulb. And think of the filament made out of tungsten, right? So there's the filament. So when you have a current going through there due to friction, you're going to get a resistive heating. So the heating is going to increase the temperatures. The resistance will go up, but it will also cause the filament to start melting a bit. So it's going to get thinner. If it gets thinner, well, then the resistance is going to go up as well. So those factors work in a cycle till eventually the filament snaps and you've lost your light bulb. Okay, the fourth law is that the nature of the material affects the resistance. As we said before, different materials like insulators offer greater resistance than conductors. And the way to, rho is spelled R-H-O, not R-O-W, resistivity is a way to designate the material's properties in terms of resistance. So it's given by the Greek letter rho, R-H-O, and the Greek letter rho is proportional to the resistivity. It's equal to the resistivity times the cross-sectional area over the length. Or isolating for resistance, resistance is the resistivity times the length of the resisting material over the cross-sectional area. The units of resistivity are ohms times meters, because resistance is in ohms, area is in meters squared, length in meters, so ohms times meters. In some older books, you'll find resistivity given in the units of ohms times centimeters. So let's see some examples of resistivity, cross-sectional area, and length. The temperature examples we won't do at this time. Okay, they're not necessary for now. So first example, we've got a resistance of 7 ohms and a length of 0.06 meters and a cross-sectional radius of 8 by 10 to minus 3 meters. If you ever see cross-sectional diameter, convert it to radius by dividing by 2 right away. So what do I want to solve? I want to solve for the resistivity. So the resistivity is RA over L. So 7 ohms times cross-sectional area, which is pi times 8 by 10 to the minus 3, pi r squared, 2.01 by 10 to the minus 4 meters squared, divided by the length, 0.06 meters. So the resistivity of the material is 2.35 by 10 to the minus 2 ohms meters. Now, if you don't know what the material is, you could perhaps be given a table with a bunch of resistivities, and you could get the best guess by matching the resistivity number with the associated material. It could, of course, be an alloy like nichrome, which is nickel chromium alloy, and doesn't have to be a pure elemental metal. Okay, second example, we have a 20 centimeter slab of a resistor and or resisting material, Again, it could be straight or it could be coiled up like in a heating coil or a coil on an element on a stove. And the diameter is 0.8 millimeters divided by 2, so you get 0.4 millimeters for your radius, which is 4 by 10 to minus 4 meters in standard scientific notation. Get the area, pi r squared, and so it's 0.503. Oh no, that's 5.03 by 10 to minus 2, isn't it? It's not a 1, that's a 2. Let's check this out here. So I'm going to take my calculator. You have a built-in pi function, right? Pi times 4 by 10 to the 4 minus squared. Scientific notation, 5.03 by 10 to the minus 7. So it's not a 1 or a 2, it's a 7. 5.03 by 10 to the minus 7. Yeah, that makes sense. So we're given the resistivity, 1.72 by 10 to the minus 8 ohms meters. So we want to get the resistance. So the resistance is rho L over A. So 1.72 by 10 to the minus 8 times 20 divided by 5.03 by 10 to the minus 7. And you get 0.684 ohms. So those are some straight calculations. You're given 3 of the 4 parameters and you get the 4th. Also interesting is if you know the length, resistance, value, and cross-sectional area for a given material, let's say silver, you can calculate the resistance for that material if it's fashioned in a different way. If it's thicker or thinner, it reminds you of like a pasta maker. You can get like really thin spaghettini or real thick cannelloni, right? And it's still made of the same flour. So we can get the resistance at a different set of conditions. And if you just divide the equation we just looked at 2 different conditions, you get these equations. R2 is L2 over L1, A1 over A2 times R1. But you can also write that as L2 over L1 and get rid of the pi's. So little r1 squared over little r2 squared times capital R1. Where the lowercase r1 is for the cross-sectional radius, and the uppercase r1 is for the resistance of conditions 1, and 2 is for the conditions 2. So let's see how it works. We got a 5 centimeter long, move up a bit here. A 5 centimeter long silver wire has a cross-sectional diameter of 0.5 centimeters and a measured resistance of 6 ohms. Calculate the resistance of a second silver wire, but this time the length is 10 centimeters and the cross-sectional radius is 4 centimeters. So it's very important, set up a little chart here. So L1 is 0.05 meters. R1 is not 0.5 centimeters, it's 0.5 divided by 2. 0.5 centimeters is diameter. So R1 is 0.25 centimeters, which is 2.5 by 10 to the minus 3 meters. And you're given measured resistance of 6 ohms for those conditions, that shape. I think sometimes of the extruder toy in Play-Doh or the Play-Doh barbershop, where you put in the Play-Doh and then you squeeze it through the toy holes and get a star or a square or different size and different shapes, kinds of things. Then you got L2 is 0.1 meters, R2 is 4 by 10 to the minus 2, and we want to get capital R2. So you plug it in, and you get 4.69 by 10 to the minus 2 ohms. Notice I squared the ratio of R1, R2, and then squared it, which is the same as squaring both, right? Is that true? Let's see. If I do 5 squared over 2 squared, that's 25 over 4, which is, just thinking something out here, 25 divided by 4, 6.25. If I do 5 divided by 2, which is 2.5 squared, it's 6.25. Yep, so that works. Okay, don't worry about that anymore. Okay, second example. Let's say I have a resistor with 5 ohms and a length of 10 meters and an area of 20 millimeters squared. I want to get the second set of conditions, cross-sectional radius, given R2 is 40 ohms and L2 is 30 meters. So let's get R1. We got A1 is 20 millimeters squared. So R1 is A1 over pi square root 2.523 millimeters, 0.2523 centimeters. Yeah, divide by 10. And I'm going to go to meters. Actually, I don't have to because all the other units will cancel, so I don't have to. Isolate for little r2. I like to cross multiply this equation here, so I get L2 times little r1 squared times capital R1 equals R2 times L1 times R2 squared, and then isolate for R2, and I get 0.155 centimeters. Okay, so this is the most algebraic way of doing it. Some of you may do intermediate steps to get the answer. Third question here, this is on the top of page 36, as I flip in my booklet here to the top of page 36. We got a copper wire, and we don't know the exact value of the length of that wire, but we know we're going to call it L1, and its cross-sectional area is going to be A1 meter squared, and we have a resistance R1 ohms. Then I have another copper wire, which is a quarter as long, so L1 over 4 meters, and the cross-sectional area is 3 times that of the first one. So we want to calculate R2. So R2 is L1 over 4, which is the same as L2 over L1. So it just becomes a quarter times cross-sectional area 1 over A2, but A2, not A2 brute, but 3A1 times R1. So it's a quarter times a third of R1. So it's a 1/12 of R1. So R2 is 1/12 of R1. An aside here, we had one, if you have a question like 7 millimeters squared, and I asked you to convert that to meters squared, it's not 7 by 10 to the minus 3, it's 7 by 10 to the minus 6 meters squared. So that's just a little aside. Be careful with your unit conversions. You got the squared there. So 7 millimeters into meters, well, that's 10 to the minus 3, but you got to do it twice because it's millimeters squared. So that's 10 to the minus 3 times 10 to the minus 3, which is 10 to the minus 6 meters squared. Okay, so that's resistivity. Now I want to look at another topic in this lecture, which is talking about work and power in DC circuits. So let's say we have a battery here and electrons flow from the negative potential, so the negative terminal to the positive terminal. They're pumped through by the battery and they do work on a load, a light bulb, an air conditioner, a speaker, whatever. So work is done by the battery on the electrons to pump them through, and work is done by the electrons on the load. We recall from last chapter that work is charge times voltage. Now we know that Q is I times T, and also we recall Ohm's law, V equals IR. So then work is I times T times V, because Q is I times T. And we also can plug in knowing V equals IR, so you get work equals I squared R times T. And we can define the I squared R as the power because we know that power is work divided by time. So power equals I squared R. We can also write power as IV or V squared over R. So electrical power can be written as any of these three equations. Which one you use depends on which one is most convenient. And there's different ways to write the work equation. Which one you use is which one is most convenient. So let's try some of these out here. And I may add a little bit to these. How many joules of work are delivered to a 120 volt bulb by 3 amps in 2 minutes? Okay, so the bulb needs a push of 120 volts. 3 amps go through it in 120 seconds, right? You got to convert the minutes to seconds. So work is ITV or VIT. It doesn't matter how you write it. 120 times 3 times 120, right? Multiplication is commutative. So 43,200 joules. If I want to get the power, power is I squared R. I don't have R yet, so let's use IV. So power equals IV. So 3 amps times 120 volts, so 360 watts. Okay, remember power is watts. And I might as well get the R here. R is V over I. So that's 120 over 3, so that's 40 ohms. So that bulb is 40 ohms. So if you want, you can write that in your booklet. I expanded upon the question there. Hooray! Okay, let's look at another one here. How many joules of work are delivered to a 100 ohm bulb by 2 amps in 30 seconds? So what should we use for work here? We got R and T. Well, we can write it as work is power times time, or I squared R times time. So 2 squared times 100 times 30 is 12,000 joules. And the power would just be the I squared times R. So 2 squared is 4 times 100, 400 watts. So that's a 400 watt bulb. It could be a halogen bulb, for example. What else could we get here? I got R, I got I. I don't have V yet. The voltage is I times R. So 2 times 100, 200 volts. So 400 watts, 200 volts. Then reminding you, electrical power is the rate of doing work or delivering energy. Power energy over time, or work over time, works well for me. I squared R, V squared over R, I times V. Units are watts. When you have a watt meter, sometimes it's drawn with a double line, sometimes it's drawn with a single line. And a watt, remember, is a joule per second. So if I have an example here where I have 34 watts and 120 volts, I want to get my current and I want to get my resistance, R. I want to get my current and I'll get my R. So I is P over V. So 34 over 120, which is 0.283 amps. And R is V over I. So 120 divided by 0.283, 423.53 ohms. And yeah, there's different orders in which you could do it. But P, I, V, R. If I wanted to get the work, well, the work I wouldn't have enough information to do that, would I? Because I don't have a time, so I can't get the work for this. Let's see, VIT, no. I squared RT, no. I don't have enough information to get the work in this example. So I can't ask that. Page 37, example 2. Let's say you're given a load which is 4 kilo ohms worth of resistance offering, which is 4,000 ohms, and 3 milliamps, which is 0.003 amps. So I want to get the power and I want to get the voltage. So the power is I squared times R. So 0.003 squared times 4,000, which is 0.036 watts. And the voltage is I times R, 0.003 times 4,000, which is 12 volts. And then you can check things. You can say, okay, is that right? I should be P over V. So if I take 0.036 divided by 12, and I get 0.003 amps, which is what I want. So that one is good. Third example, I'm given 120 volts, 12 ohms. I want to get the power and I want to get the current. So power is V squared over R. So 120 squared divided by 12, which is 1200 watts. And I is V over R, so 120 over 12, which is 10 amps. So there is my power, current, voltage, and resistance information for that question. Fourth example, let's say 6 joules are delivered to a 1 ohm resistor in 1 minute. 1 minute, of course, being 60 seconds. We want to calculate P, I, V. We got R, we got the work, 6 joules. So the power is the work over time, 6 joules over 60, which is 0.1 watts. Good. And then my power is I squared R. So I is the square root of P over R. I just got the power, 0.1 watts divided by 1 ohm. So I get 0.316 amps. And then the voltage is IR, or P over I. You're going to get the same answer, 0.316 volts. Okay? So those equations, you have to become an expert with that. Now, when you're looking at a circuit, you add together the power to get the total power. It doesn't matter if it's series, parallel, or network. You add up the power used or dissipated at each load or actual resistor, and the total power is the sum of the power dissipated at those. So in this first example here, and this gives us some more practice with our circuit diagrams, example 1, so we got a severe with a P at the end, severp, if you will. So I got 5 volts, 10, R1 is 10, not 16, R1 is 10 ohms, R1 is 10. R2 is 6 ohms, so the total is 16. My voltage is 5, so my current is 0.3125 amps going through the whole system. So that's 0.3125 amps through R1 and 0.3125 amps through R2. So then the voltage is across each is I times R, so 3.125 and 1.875. You add together R1 and R2 to get our total. And then the power, when I get the power in the severp diagrams, it's fastest just to do I times V, right? Then you aren't doing any squarings, and you're just really quick. So you get 0.976, 0.5859, the total 1.56. And you see that if I add together R1 and R2, I get R total. So that works good. Example 2 is a pure parallel case with one resistor in each branch. 12 is my given voltage, so that means there's 12 volts across each resistor 1, 2, and 3, and my resistances offered are 10, 40, and 80. So my equivalent resistance is 1 over 10 plus 1 over 40 plus 1 over 80, and you take the reciprocal, and it's 7.273, and I is V over R, 12 divided by 7.273, which is 1.65 amps. Okay, so then we have these 3 branches, and we see that the path of least resistance is R1, just 10 ohms, and lo and behold, more of the current goes through there, right? That's what we mean by path of least resistance. It's just like when you're walking down the hall at school. Remember doing that? And there'd be 2 doors, and everyone would like to try to squeeze through one door because they wouldn't want to open that double door near Mr. Stevenson's office. And but if you do open it, then this path of least resistance, and well, no, keeping that door closed means it's more resistance. So more people try to go through the thing that's already open. Great. So then I can get the power through each, power through resistor 1, resistor 2, resistor 3, add them together, and I get 19.8 has my power dissipated in example 2. So power again is additive. And here we have the third example. My dogs are very excited about this third example. It is a network. That's why they're so excited. So you have R1 and you got R2 and R3 in parallel. So we can get the equivalent resistance of R2 and R3, and then add that to R1 to get the total resistance. So my total resistance is 6 volts. And suppose you're given R1, R2, and R3, 1, 1.5, and 1.8. So I can get the equivalent resistance, R23, take the reciprocal of 1.5 and 1.8, and you get 0.82. Add that to the series R1, so my total resistance is 1.82 ohms. My current then is 6 divided by 1.82, which is 3.3. So that's the same current that flows through my fictitious resistor R23, 3.3, and my R1, which is also 3.3. Then when I branch from R1, right, I'm branching into R2 and R3, more is going to flow through R2 because it offers less resistance. I know that the voltage is the same as R23, 2.71. So my current is 2.71 over 1.5, which is 1.81. And across R3, 2.71 over 1.8, which is 1.51. So that is how that works. And the power is I times V, so get all these powers. Now let's see here. My total is 19.8. So if I add up R1, which is 10.9 and around 5 and 5.99, yeah, 19.8. You don't add R23 in, because R23 is not a real resistor. But if I add up the powers dissipated across R1 and R2 and R3, I can get the total power associated with this circuit. Okay? Now, is this one last topic or two? Let's see. This is going to be the cost of power. No, there's one more thing after that. That's fuses. Okay, well let's push ahead and do them both. Why not? So, we sometimes give energy in units of kilowatt hours. That's what we're buying. When we buy from Manitoba Hydro, we aren't buying power. Even though it's called a power company, we are buying energy. And you know that work is power times time, because power is work over time. Let's write that and remind ourselves. So this is a new topic. Still, everything's all related. Power is work over time. So work is power times time. So for example, kilowatts times hour. And a kilowatt is 1,000 watts, and an hour is 3,600 seconds. So a kilowatt times an hour is the same thing as 3.6 by 10 to the 6th joules. Now that's going to help us as we go through some of these questions here. So let's say you have a fridge and the rating on the fridge is 20,000 watts, 20 kilowatts, and you're running the fridge for 5 hours. What's the energy involved in units of kilowatt hours and in joules? So the energy, which is the work done, you do work to cause a change in energy, is power times time. So it's 20 kilowatts times 5 hours, so 100 kilowatt hours. Sometimes you see a little dot between the W and the H, but you don't have to. And I can just multiply by 3.6 by 10 to the 6th, so that's 3.6 by 10 to the 8th joules. Now suppose you're told in part B that it costs, this is question 1, part B now, this is question 2. Suppose it costs 5 cents per kilowatt hour. What's the cost to run the fridge? And I'm going to assume that the cost is a fixed number per kilowatt hour. You might not be surprised to know that kilowatt hour rates change depending on the time of day. So the money, all you do is you take your power times your rate. So your kilowatt hours times your money in kilowatt hours. So 100 kilowatt hours times $0.05, right? 5 cents is $0.05. So that becomes $5. So $5 is the cost to run the fridge for 5 hours. Seems like a lot of money. But anyways, we just put in the numbers. In general, cost is the power in kilowatts times the time in hours times the rate in money per kilowatt hours. Don't just say money, but money per kilowatt hours. So let's get a practice on how to do that here. In example 2, electric heaters, very dangerous items. It's 200 watts and 117 volts. We want to calculate I, R, and P. So the current, I got the power, 200 divided by 117. So the amperes flowing through the heater calculates to be 1.71 amps. The resistance of the heater coils, V over I, so 117 over 1.71, which is 68.42 ohms. The power I already know is 0.2 kilowatts. Why do we care about that? Because look at the next question, part B. If the heater runs continuously for 1 day, calculate the energy in joules and kilowatt hours. You got that heater on continuously, so I got 200. No, I don't want to say that. 24 hours. This should be 0.2. 0.2 kilowatts times 24, 48. 2 times 24, 48, 4.8 kilowatt hours. So 0.2 should be my power. So 4.8 kilowatt hours, and I can multiply by 3.6 by 10 to the 6 joules per kilowatt hour to get 1.73 by 10 to the 7 joules. That's not that important, though, in the next question, because the next question gives you the rate. Your money rate has 7 cents per kilowatt hour. So to run that heater, you're going to take 4.8 kilowatt hours times $0.07 per kilowatt hour. So it costs you 34 cents to run that heater for 1 day. And we're lucky in Manitoba to have rather inexpensive rates for power. Okay, so you should be able to handle questions where we talk about money. And if you look at new appliances, they all have these Energy Smart ratings. And now when you read those, you'll understand more how they work. Okay, so related to power and current and all this good stuff, additivity, is the concept of a fuse. And a fuse, the schematic symbol, is just this little sine curve with the dots here. Don't see, hey, I put a circle around it. I shouldn't have put a circle around it because then it makes it into a generator. So I'm not going to put a circle around it. There, I'm going to redraw it like that. So a fuse, you'll find them in cars. You'll find them in really old houses, fuse boxes. Now they're called breaker boxes, but in the old days they were called fuse boxes. Someone loses their temper, they blow a fuse, just means the fuse snaps because there's too much current going through it. So they're a safety system. And you have them in stereos, for example, so there's a big surge of electricity, the fuse snaps, and the juicy, really good, expensive electronic stuff gets saved. So fuses are short pieces of metal that melt from heat released when current flows through them. Too much current. The fuse ratings, typical ones, in stoves, for example, are 15 amps, 20 amps, 25 amps. They're smaller in cars. Depend on the kind, thickness of the metal. And the fuse rating is the maximum amount of current that can safely flow through a circuit. So if you have a 20 amp fuse, you can have 20 amps flowing through it. You can have less, but you can't have more. If you try to push a 20 amp current through a 15 amp fuse, the fuse is going to melt. And a practical thing here is always match your fuses when you have to replace them. A lower rate fuse shouldn't be replaced with a higher rate fuse, because if you do that, you're going to end up having too much current going through, and that could be a fire issue. And you don't want to replace a higher rated fuse with a lower one, because then your machinery won't work properly. So you should always match the fuses when you replace, upon replacement. Okay, so let's say I have a 110 volt circuit. So there's example 1, 110 volt circuit, and I got several fixtures possible to be plugged in, and the fuse is at 15 amps. By the way, some people in the olden days, they bypass fuses. They'll use, if they know a little bit about wiring, they'll do dangerous things like hammer and nail to bypass a fuse. Well, if you do that, yeah, you can draw more current, but you can also burn your place down. So don't do silly things with electrical wiring. Either learn to become an expert and get a license in it, or hire someone to do it. But don't futz around with, pardon my language, with wiring yourself if you don't know what you're doing, because it can be tragic consequences. Okay, so let's say we have in our kitchen 15 amps fuse, 110 volt circuit, and I put in a 1000 watt toaster and a 400 watt electric kettle into the same circuit. Will I blow a fuse? Well, if I burn the toast, I sure will. And if I don't, how many watts will I have left over? So my maximum is 15 amps. My total power, well, I have a 1000 watt toaster and 400 watt kettle, so that's 1400 watts. So the voltage is what is the voltage? P equals IV. Did I have 110 volts? No, P equals IV. So V equals P over I. So 1400 divided by 15 is 93. That's not right. Let's see. How am I getting V total is 110? Am I? Oh, it tells me that. It tells me that 110 volts. My total voltage is 110. So my current is my total power, not my maximum power, but the total power from the appliances in there, which is going to be 1400 divided by 110, or 12.73 amps. 12.73 amps. My maximum power is how much current can I go through altogether? That's 15 amps times the total voltage 110, 1650. Well, so I have some watts to spare. I have 1650 minus 1400, 250 watts to spare. The current I have to spare would be I to spare, which is going to be my leftover power, 250 divided by 110. 250 divided by 110, which is going to be 2.27 amps. And then you're going to say, well, of course it's 2.27 because your maximum current, as dictated by the fuse labeled on the fuse itself, perhaps is 15 amps, and 15 minus 12.73 is 2.27. So 15 minus 12.73 is 2.27. Okay, so I was given the 110 volts. That got me tripped up a bit, but I think I reclaimed my question there and explained things well. If I didn't, let me know. Send me an ESB saying you want to look at it again. Okay, now that was just two objects, so we didn't blow a fuse. We were getting a little close to it, but we could have put in more stuff, but not more than 250 watts. So if I put in a 300 watt light bulb, then I would have blown a fuse, tripped the breaker. Now let's say we started over, but this time we had a whole bunch of stuff put in. 150 watt electric blanket, a 40 watt radio, 400 watt lamps, a 3 watt calculator, a 60 watt electric foot massager. Well, that's lots of stuff. Well, but none of them draw that much power. I'm not going to draw, what's the maximum power? 1615 watts, which would be my fuse rating, 15 times my voltage of the circuit 110, 1650. If I add these all together, I get 150, 190, another 590, 593, 653, which is a lot less than 1650. Okay, and you know this from those of you who hang up holiday lights, Christmas lights, for example. You're going to get that. Oh, the dog just got in the groceries. Dog, get away from the groceries. Okay. Oh, the dog just wanted to get a popcorn twist. I tell you, they're hungry. Okay. Anyways, so the fuse isn't going to blow. I can put more stuff in. But yeah, if you have holiday lights, then you can put lots and lots in without blowing a fuse because each light does not draw that much power. Okay. So here's a review on page 40. Some of the equations that we have: I equals Q over T, Q equals I times T. I got the work, VIT, I squared RT, power times time, V equals IR. Then I got the power equations, energy over time, I squared R, I times V, or V squared over R. Then I got the resistivity equations, R equals rho L over A, or the same material in different shapes, which is the R2 L2 over L1, A1 over A2 R1, or then that shorthand way where I get rid of the pi, so R1 squared over R2 squared. Cost of energy, power times time times the rate, power in kilowatts times in hours times the rate in money per kilowatt hour. Using kilowatt hours is just a convenient way of doing things. If I'm using joules, I got to use scientific notation, and the general public doesn't like to use scientific notation. Going back, we had resistors in series, and we had a set of rules for that. resistors in parallel. Did I write V equals IR anywhere? Yeah, I did. Yeah, of course, Ohm's law, good. Diameter is 2 times R, area, cross-sectional area, pi r squared. Batteries in series, just add the voltage, we mentioned that. And here's some schematic symbols. A cell, an open switch, fixed resistor, variable resistor, fixed capacitor, variable capacitor, a lamp, an ammeter, a voltmeter, an ohm meter, a watt meter, parking meter, the ground, just a straight line is a conductor. Okay, so those are all sets of equations. Then there's some questions, but I'm going to hold off on those questions and do a review class for our next and final lecture on Unit 7. Okay, sounds good. Now I just have to figure out how